हाँ सर हो गया। जाए तो दो ही उसके बाद वाला चलना नहीं है मार्क्स वाला कर दो। ठीक ठीक कर शेयर कंटेंट। Hello, can you hear me? Hello,
Good afternoon, sir.
good afternoon. हाँ
Yes, sir. Are you here?
आ रही आवाज आ रही है ना बस
Yes,
ठीक
sir.
है।
Yes, sir. Are you?
Today I'm going to talk about non-linear models, fitting of non-linear models. Actually, fitting of a distribution using ML method is also a problem of non-linear optimization. Fitting of distribution is very simple task in R. We shall use the function optim for maximum likelihood estimation. This function returns negative of the Hessian matrix provided negative of log likelihood is the objective function to be minimized. It is a well-known fact that if Li theta is the log likelihood for ith observation and L theta is the likelihood for n observations, then L theta is equal to summation of Li theta. Thus, maximum likelihood estimate is obtained by minimum of minus L theta. And Hessian matrix is equal to minus L double dash theta at theta is equal to theta cap, which is nothing but Fisher's information matrix. This is the second order partial derivative of log likelihood, which is termed as Fisher's information matrix. It may be noted that asymptotic variance of theta hat is I inverse theta hat. That is the Hessian Fisher's information matrix at the observed point. This implies that the standard error of theta hat is square root of diagonal element of this variance covariance matrix. Thus, 100 into 1 minus alpha percent confidence interval is theta hat plus q norm alpha by 2 lower dot tail is going to false into standard error of theta, where standard error of theta is diag sol I theta. So this is the theoretical background. Now I'm going to talk in terms of how to implement these things using optim. The optim, the function optim, whose first argument is parameters, the guess value of the parameter, fn, the function to be minimized or maximized, Hessian is equal to true, is a logical variable. If Hessian is equal to true, then it returns Hessian matrix also. Available with R core team, that is base R, is meant for nonlinear, unconstrained optimization, preferably minimization. It requires the value of the parameter, that is argument par and objective function minus L theta. The argument Hessian is equal to true is required to return Hessian matrix at the optimum point. The three dots, three dots here at the end in the argument stand for arguments which are not specified. Now, fitting of exponential distribution, this is a very simple problem. This is the distribution, which is nothing but dexp. This is the value of the density. Y rate is equal to lambda. This implies that log likelihood for exponential with rate is equal to lambda is Li theta is equal to log of Fyi given lambda is equal to log of this expression, log of lambda minus lambda yi. This implies L lambda is equal to summation of Li lambda is equal to summation of log of this. And this is nothing but sum dexp y comma lambda log is equal to true. Log is equal to true returns log values of these things. Now, fit exponential distribution set dot seed. We are simulating 20 observations with rate is equal to 0.03, and these are the 20 observations from exponential distribution. And now define negative likelihood, negative log likelihood, negative of log likelihood of exponential distribution. And LLE is equal to function of theta y, and then inside the curly bracket, LL is equal to log likelihood is equal to DEXP y rate is equal to theta log is equal to true. Then L is equal to sum of LL and return minus LL. Dump the file. Now to fit this distribution, M1 is equal to optim par is equal to 0.01. Because we know that the value of lambda is 0.03, so we are having a guess value to start iteration 0.01. Fn is equal to NLLE, this function. Hessian is equal to true, method is equal to LBF GSB, lower is equal to 0.001, and Y is equal to Y, because par is used to optimize with respect to this, and the other argument Y is equal to Y that provides the data. And this is the value of the maximum likelihood estimator. This is the value of the objective function, and this convergence 0 means it is effective convergence. Then Hessian matrix. So MLE is equal to M1 par ML estimator, and standard error is equal to SQRT diag solve. This is the inverse of the Hessian matrix, SC for theta, and this is the standard error of theta, MLE, and this is the standard error of theta. Now we can recognize them out R bind, row wise binding, MLE and SC. Column names C is equal to rate. And when we will put out, this will be the result. MLE, R, because of R bind, MLE is here, row wise binding, standard error is here. And the column name is rate. So this is the estimator, and this is the standard error. Fitting a Weibull model. Weibull distribution is very popular distribution for fitting of reliability and survival data. It has a shape and scale parameter. It is fitted as y is equal to r Weibull. We are simulating 30 observations from Weibull with shape is equal to 1.5 and scale is equal to 50. And then we are computing negative of log likelihood and LLW. Negative of log likelihood of Weibull is equal to function theta comma y, and LLD Weibull y shape is equal to theta 1, and scale is equal to theta 2, and log is equal to true. And LL is equal to sum LL and return minus LL. Then up to optim par. This is the guess value to start iteration. For shape parameter it is 1, for scale parameter it is 30. And Fn is equal to, this is the objective function to be minimized. Hessian is equal to true, method is equal to LBFGS, and lower is equal to C 1.2. Actually, both the parameters are positive, so we are giving positive values we are restricting this to the positive values. Y is equal to Y, M1 par, and then standard error is equal to SQRT diag sol M2 Hessian, and then out R bind MLE SC. These are the row wise MLE and SC, and column names out C is equal to shape, and second column is scale. So this is the MLE of shape parameter. This is the MLE of scale parameter. This is the standard error of MLE of shape, and this is the standard error of MLE of scale parameter. It may be noted that the fitted value are in close agreement with the true value, which shows the strength of fitting procedure. Because our guess value, our simulated value has the shape 1.5 and this value has 50. Assignment. Fitting of a nonlinear regression model with Optim. Now we can make use of Optim to fit a nonlinear regression model. We can fit a nonlinear regression model using Optim. For example, we can fit a growth model defined as weight is equal to beta naught into beta 1 raised power h plus epsilon for growth data of chicks, weight, and age defined as chicks read that table. So this is the data. This is the data on chicks age of embryo, and this is the weight. Define a model in R. NLL rig, negative of log likelihood rig. Function theta y x. Error is equal to d norm, because we are assuming that normal distribution is the error. So dl norm theta 1 into theta 2 raised power x, and then the other parameter sigma is theta 3 and log is equal to 2. Then LL is equal to sum LL, return LL. Fitting using Optim. Y is equal to chick's weight, X is equal to chick's age, and M1 is equal to Optim par is equal to, these are the guess values of beta naught, this is beta 1, and this is sigma. Fn is equal to NL rig, Hessian is equal to true, Y is equal to Y, X is equal to X. And these are the parameter estimates, maximum likelihood estimates. These are the estimates, and this is the value of the objective function at optimum point. Converge 0 means it has good convergence, and then this is the Hessian matrix. And from this Hessian matrix, this is ML par. So these are the maximum likelihood estimator. And to compute the standard error, SQRT diag solve M1 Hessian. Out R bind row wise binding MLE and SC. So this is the estimate of beta naught with the standard error, estimate of beta 2 with the standard error, beta 1 with the standard error, and this is the value of sigma. Fitting with fit star of mass package. A very powerful function fit star is available with mass package due to replay 2024. A large number of distribution can be fitted using the function, using this function fit star. This includes normal, Poisson, T, gamma, etc. It can be reported as fit star x. X is the name of the function. X is the data, and DES function, this is the density function, and this is the start values, with where X stands for the data vector to be fitted, dense fun stands for the name of the density to be fitted, start stands for guess values to start iteration. Let us begin with the gamma distribution. So library, this is X is equal to R gamma. How 100 observations are being simulated with shape is equal to 5 and rate is equal to 0.1. Then fit the star X comma gamma. So this is the estimated value of shape and rate, and then this is the standard error of shape, and this is the standard error of rate. Now do this directly with more control. Fit the star x gamma list shape is equal to 1, rate is equal to 0.1, lower is equal to 0.001. Again, the same result we get. Assignment. Fitting NLS nonlinear models. The function NLS available with R core team, that is, it is a part of base distribution, function, formula, data, actually, then algorithm, default, bilinear, port. Here, the first argument specifies the formula of the nonlinear model. Second argument talks about data from which data is to be called. Third argument talks about the starting values for the iteration. Let us x is equal to 1 is to 10, y is equal to twice x plus 3, and YESP. This is the response. This is the response y plus r norm length as equal to this thing. NLS, this is the YESP versus a plus bx start is equal to a, starting value of a is this one, b is this one, and this is the value reported. A is equal to 3, b is equal to 2, and we already know that a is equal to 2 and b is equal to 3 here. So same results we are getting. A is equal to 3 and b is equal to 2. So we are getting the same result. Another example of nonlinear function, x is equal to this. We are simulating the data for x, and then we are simulating the data for y, and then model NLS y. This is constant plus a into e raised power b into x, and see, this is the result. This is the value of the constant, which is 100 there, and here 99.99, and b is equal to a is equal to, actually it is a is equal to 10, so 9.92, and b is equal to 0.5, so it is 0.4975. And then we can plot this data, plot xy main is equal to NLS data, true function, fit star, curve, and color is equal to green, add is equal to true, lines, x predict, NL mod, color is equal to red. So these are the observed data, and this fitted line is the red line. Modeling of chicks embryo weight with NLS. Just, do you have any problems? Do you want to ask something? Please interact with me. Do you want to ask something?
No, sir.
So then I'm continuing.
Okay, sir.
Modeling of chicks embryo weight with NLS. This chicks embryo data we have already discussed. We have used opt-in, but now we will make use of NLS. Chicks data has been discussed in one of the great books on data analysis. That is Sandeker and Cochran, 1967, Statistical Method, Iowa State University Press. So we are reading the data from a text file, and this is the data, age column and weight column. Now M1 is equal to NLS weight. Actually, the model is being fitted here. This is the formula weight modeled as beta naught into beta 1 raised power age. Data is equal to chicks. Start beta naught is equal to 1, beta 1 is equal to 1. And this is the summary of results. This is the beta naught estimate of beta naught. This is beta 1. This is standard error. These results are in close agreement with the results we have obtained with opt-in. And this is the t value. Divide this by this, it is t value. Divide this by this, it is t value. And this t value shows that they are statistically significant because p value is much less than 0.05. It is 4.23 into 10 raised power minus 5. 1.66 into 10 raised power minus 5. And then we are plotting weight versus age. Data is equal to chicks. Then curve we have added and lines checked. See here, we have added the curve in black, and then we have added the predict value, and that is same. They are one and same, and that's why they are indistinguishable. Fitting of linear, quadratic, and exponential log-log model. This iron slag data available with dark package is a data frame which has 53 rows and 2 columns on measurement of iron contents obtained from iron slag by using two methods, chemical or magnetic. A scatter plot of the data suggests that chemical and magnetic variables are positively correlated, but the relationship may not be linear. From the plot, it appears that a quadratic polynomial or possibly an exponential or logarithmic model might fit the data better than a line. Thus, proposed models for Y magnetic measurements versus X chemical measurement are here. M1 is equal to log linear, M2 is equal to quadratic, and M3 is this nonlinear model, M4 is also a nonlinear model. So this is the data, and we are fitting NLS chemical versus beta NLS chemical versus not plus beta 1 into magnetic. So this is the linear model, and we are getting the result. And then we are fitting chemical versus beta naught, beta 1 plus beta 1 into magnetic plus beta 2 into isolated magnetic. This is the curvilinear, and this we are getting the result. We are getting the result. Here, curvilinear coefficient is not significant, whereas beta naught is also not significant, whereas beta 1 is significant. Then, fitting M3 model, chemical versus EXP beta naught into EXP beta 1 into magnetic, start, and these are the results. Here, both the coefficients are significant. Then, fitting M4, NLS chemical versus exponential. So, we have fitted actually the non-linear form of the model. We have not made it linear. And these are the results. Comparing three models using AIC. AIC of M1, that is the linear model 286.05. Then AIC M2 quadratic 286.69. Here AIC of linear model is somewhat less than that of quadratic. But AIC M3, it is 288. It is bigger, and AIC M4 is 285. So this is the M4 is the best model, log linear model. It is thus on the basis of AIC model M4 is the best because it has least AIC. Looking into graphically, so these are the commands, and these are the M4 fits the best. M4 fits the best. Now the problem of starting values. Choice of starting values is a problem sometimes that can be solved using the function SS for logistic growth model. Data ELISA assay of DNAs. The DNA's data frame has 176 rows and 3 columns of data obtaining during development of ELISA assay of the recombinant property DNAs in rat serum. So name DNAs, and using self-start function, we have DNAs 1 subset, DNAs run is equal to 1. We have selected a subset of data with run is equal to 1, and we have fitted that NLS density versus SS logis, and these are the parameters of the model, and these are the results. All these parameters are then compare with the 4-parameter logistic model. This is the 4-parameter model. One parameter has been added, and then ANOVA. The first one is 3-parameter model, second one is 4-parameter model, and this p-value 0.65, which is not less than 0.05. This shows that the FM2 model is not better than the first because there is no significant improvement. Weight loss data, mass weight loss. Here, weight loss data from an obese patient. The data frame gives the weight in kilogram of an obese patient at 52 times time points over 8 months period of a weight rehabilitation program. So these are the days and these are the weight. And the model for this data is proposed like this. Fx beta naught beta 1 beta 2 is equal to beta naught plus beta 1 into 2 raised power minus x by beta 2. So we have fitted this model here, and as is modeled as beta naught plus beta 1 into beta 1 into 2 raised power minus days by beta 2. And these are the starting values and these are the results. These are the results. And plot this plotting as days increases, the weight also decreases. So this is the plot. How to define a function and calling into NLS. See here, ultrasonic calibration data 2. This is the ultrasonic calibration data 2. Here, plot y versus x data is equal to chain root 2 x lag. So this is the data. And we have proposed a model, a nonlinear model to fit this data. This is the nonlinear model. And then we have defined x fact function, x, beta 1, beta 2, beta 3, and then we are writing this expression, fitting this model with using NLS. NLS y versus exp, we have given the argument, and data is equal to chain root 2 and start. These are the starting values, and getting the summary of results. These are the summary of results. So all the 3 parameters are statistically significant. It is evident from the names, and then name summary. So all these things could be extracted. Graphically looking into the matter, so here we have plotted the data, we have got scatter diagram, and then we have a plot of fitted data, and this looks a very good fitting. Using function for growth model for chicks. See here, we have defined this as a growth model. We have defined this growth model, exp chick function x beta naught beta 1 and beta naught into beta 1 raised power x. And we have fitted this exp, and data is going to chicks start is going to this thing. And we are getting the same result which we have obtained earlier. Looking graphically also, it looks like as age increases, weight also increases, and this model fits good because most of the points are around the line. Then references. This is the reference of a language and environment for statistical computing. This is the reference of base R, and this is Ripley Region 2024 mass. This is the reference of the mass package. So this all I wanted to discuss today. So do you have any problem to discuss with me?
No, sir. There is no problem.
So are you following each and everything? You
Yes,
should
sir.
go through these. Are you going with the commands also?
Yes, sir.
Hmm.
सर एक क्वेश्चन था सर कि जैसे सर
हाँ
बहुत सारा फंक्शन है सर, वो याद तो नहीं हो पा रहा है, तो ऐसे सर कौन सा वीक से ज्यादा क्वेश्चन आने के चांसेस है सर?
बेटा, बहुत सिंपल सिंपल से क्वेश्चन पूछे गए हैं, मुझे याद नहीं है कि किस टाइप के क्वेश्चन पूछे हैं, लेकिन बहुत सिंपल सिंपल क्वेश्चन पूछे गए हैं।
ओके
अगर
सर।
आपने इसको पढ़ लिया एक बार
यस सर।
तो इंशाल्लाह एग्जाम में अच्छा कर लेंगे।
चलिए,
हम्म,
थैंक यू सर। कल ही एग्जाम है सर, कल सुबह ही हमारा एग्जाम है सर।
अच्छा अच्छा, ठीक है बेटा। गुड लक गुड लक।
थैंक यू सर।
ठीक है, हम क्लोज कर रहे हैं आप।
ठीक 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 है सर।